everyone. Thank you for joining me at this month's HPC Cafe. My name is Anna, and this afternoon we are going to talk about the molecular dynamics package Gromacs. We will start with a short overview of the history, then I will share some of our benchmarking results, and in the end we will see how to use Gromacs on GPUs and CPUs. Gromacs was first published in 1995, and its functionality is based on another molecular dynamics simulation package, namely the Gromacs. A lot of the functions were copied, but also a lot of new algorithms were added. The word Gromacs is an acronym for Groningen Machine for Chemical Simulation. And this was actually a physical computer, a processor ring that ran the MD simulations. In the beginning, there were only 2 force fields available, but the designers and developers were able to run, well, 1 nanosecond in 3 days. But for the beginning, this was totally cool. Then we'll go on. New versions were published and another force field was added. And what's actually quite nice about the new developments is that the developers used the multimedia instructions on the processors that are there for lightning processing in games and could use this feature to calculate the distances, the interparticle vectors between pairwise distances from particle coordinates. I'm not going into detail what the developers then added. They added OpenMP, multi-threading, and ported the code to GPUs, and even more developments on GPUs, transition to a different language. And in the end, we end up with version 2022 that improves the direct communication on the GPUs. That's all about the history. We can offload a lot of calculations from the MD steps to the GPU, and by that, the performance can be increased. Now let's look at some of the benchmarks. The first case I'm going to show you is a standard all-MD simulation. It's just a protein in a membrane and with explicit water. All of the possible calculations are offloaded to the GPU. These are the numbers that I produced, and we can see that by quadrupling the number of the GPUs in the first line for Gromacs 2019, we get up to 96 more nanoseconds per day. This is about a performance increase of 72% than with only 1 GPU. But if we look at the line with Gromacs 2021.1, we get for 1 GPU 233 nanoseconds per day, which is actually the same as with Gromacs 2019 on 4 GPUs. So the take-home message here is use the newer version if possible, because we can get the same increase in performance when we use the newest version as compared to just using multiple GPUs. Now, the reason why the performance on 2 GPUs is actually lower than on 1 GPU is because the update functionality only works with updates groups and with hydrogen bond constraints, and not all bond constraints. So this is something I'm going to talk about later, but it is something to consider to only use constraints on hydrogen bonds and not on all other bonds. The newest version is not completed yet, so the performance data is not that good at the moment. So I would recommend to use the Gromacs version 2021.5 at the moment, but we need individual tests to gain an impression of the actual performance per system. This is the same case. It's also the offload of every calculation on GPU. And what we can see here is that the newest generation of GPUs yields the best overall performance because the GPUs also improved the architecture. There are more cores available, the communication is better. What we can see here again is that when we increase the number of GPUs, we might only gain 2 nanoseconds of performance increase. And this doesn't make sense, right? Why should we use more GPUs just to get 2 nanoseconds? Below the nanosecond is the parallel efficiency, and this is the ratio of the speed up, which quantifies how much faster we can compute with more than one device. And it tells us which fraction of the resources is actually used for computation. So in this case, 1/4 of the hardware is used. We use 4 GPUs and we get the same performance as for 1 GPU. So even if we use 4 GPUs, basically it's only 1 GPU. And this is the same for all of the other examples I showed you here. In nanoseconds, the increase is 63 nanoseconds per day, but the parallel efficiency is still 0.3. So that means it uses still less than half of the hardware. It doesn't make sense to do this. Here, the same for the RTX 3080, and again, also for the 2080 Ti. The overall message here is don't do this. It is a waste of resources, and the hardware is too costly to do this. So don't use multiple GPUs if you know that your performance doesn't increase, or just slightly by a handful of nanoseconds. Let's look at another case. This is also a protein in a membrane surrounded by explicit water. And I benchmarked it on GPUs and CPUs. We all, again, offload every possible calculation to the GPU. And on the CPU, we need to optimize the number of threads dedicated to the particle mesh eval, so the electrostatic calculation, the thread MPI, if we use it on one CPU, and the open MP settings for shared memory. Here are the performance numbers for the GPUs, and we can see here that regardless of the age or the architecture, so Volta or Ampere, the benefits are the same nearly. We can increase the performance. I'm going to show you the CPU data as well. So we can increase the performance on the GPU as compared to one node of the CPUs. In addition, the scaling on CPUs is not perfect because we lose about 10% of performance each time we double the number of CPU nodes, because those CPU nodes have to communicate with each other, and this overhead is lost for our actual simulation. This is to show you that the simulation on an RTX 2080 Ti GPU is a bit higher than the same simulation on 12 meganodes. And 12 meganodes are or were much more expensive than one GPU node. So if you can, use the GPUs instead of the CPU cluster. This is a comparison between the 16 nodes on Maggie the newest GPUs, the newest architecture with the A40, and our new Fritz cluster and the Hawk hardware, and the performance is virtually the same. And again, the GPU nodes are less expensive than the CPU nodes. And it's easier to use a GPU with Gromacs because you don't have to do the tuning to use as you should do on the CPUs. Here we have more benchmarking systems. We start with the category of small systems. The first one is organic molecules in hexane, which is also an organic molecule. And it's quite small, but it has a very high output rate. This is needed in this case, but let me tell you, it slows the performance. When we compare the values for system 1 between the GPUs A100, V100, and the RTX GPUs, there is not really a difference. So in this case, you might want to use an older GPU because there is no gain in using the newest ones. For the A40, actually, we see a slight advantage, which is probably caused by the combination of single precision peak performance and the more powerful host than compared to the RTX 3080. And also the simulations are run with the data on the local hard disks. And for the system 2, which is just around 32,000 atoms, but with a normal output rate, I say I'm going to show you in the end what I mean by a normal output rate. Again, we can see here that it doesn't make a difference if you use the old RTX GPUs or the new RTX GPUs. The speed up is mostly the same here. But again, the increase for the A40 and the A100. These two benchmarks, they show you that you should choose the optimal hardware setup for your system, and it depends on size and type and output. So these systems are nearly the same in size, but the output rate decreases the performance in system 1. And here is the take-home message. Make sure to only write the amount of data you actually need. Don't write more just because you think more data is better. If you don't need the data, just don't write it. Too much output decreases your performance. In general, please use TinyGPU for those small systems. But this is our recommendation. You don't have to, but you probably get a ticket. And so you don't have to wait in the queue for too long on GPU. Just write the SBatch GRES GPU 1 into your Slurm script, and then you get access to a random GPU. Let's now go to medium-sized systems. These are the most popular on our clusters. And we can see here that for those, so these are the sizes I showed you in the beginning with case 1 and case 2. So the performance across the Volta generation, which is the 2080 and the V100, is quite similar. And the results for the Ampere generation, they are nearly identical. In this case, it doesn't make any sense to use the V100 because you don't need double precision most of the times in your Gromacs calculations. So just use the GPUs that can do single precision. Also, the performance on the V100 is not that perfect for these types of simulation. Again, the performance depends on the host CPU, which is why the RTX 3080 performance is it is as expected because the CPU is weaker. And here we can also see that if we double the size of the system, our performance decreases by half. The message here is you can use either the A40s in Alex or use the GPUs available in TinyGPU, but also be aware that the number of CPU cores makes a difference, can make a difference to your simulation. If you use TinyGPU, you can again add the line to your Slurm script to get a random GPU. So let's go to some large systems. These have 500,000 and 1 million atoms. Not many of our users look at systems that large on a regular basis, but there are some that do. Here, our recommendation is not 100% clear, because these simulations can actually benefit from a multi-GPU setup, but that has to be checked for every case. So you need to do benchmarking to find out whether you can use multiple GPUs or whether you lose performance if you do. Again, here's only, again, a small difference between the RTX cards and the V100, but there is an obvious increase in performance when switching to the large systems. The A40 and the A100 are the Ampere architecture, and they have a great number of CUDA cores and a large memory bandwidth. And also we have a large number of CPU cores per GPU in those nodes. So the performance here increases for the large systems. But please perform benchmarks to find the best hardware and check if performance increases with multiple GPUs. Are there any questions so far? All right, then we'll continue with how to use Gromacs on our clusters. You can find the new Gromacs version by typing, so you have to log onto our front nodes, obviously, and then type module avail Gromacs, and then you will find a list of all the modules we have available. You can load the modules with module load, and then copy the name of the module. Modules containing CUDA can only be loaded on the GPU nodes, and it might make sense to log into a node, load the module, and then see how the MD engine is named or do some benchmarking. You can't do GPU benchmarking on the front nodes because the front nodes do not have GPUs available. So the MD engines are GMX MD run and srun, GMX MPI MD run. They are also, you can find them in our documentation. For the thread MPI versions and the real MPI versions, then add the run input file with the S flag. Decide if you want to give your simulation output a name, a new name. And the most important, do not use the verbose output because it writes through the network into your home directory, and you might be a victim of NFS latencies that might decrease your performance. So only use the verbose output if you need to debug a crash simulation. Let's go on to different GPUs. I know this is a long command line, but just copy and paste it. The most important thing here is that with NT-MPI, you add the number of thread MPI threads. That has to be equal to the number of GPUs you use, and the flag NT-OMP for the number of OpenMP threads per MPI rank, and this should be the number of cores available for the GPU. I have a slide on that later. For TinyGPU, I've already showed you, use the SBatch GRES GPU1 in the Slurm script. And for Alex, the NT-OMP should be 16 because there are 16 physical cores per GPU available. On TinyGPU, it depends on the hardware. So for the RTX and the V100, it's NT-OMP 8. And for the GTX GPUs, it's NT-OMP 4. The usage on multiple GPUs, please only do it if you have large systems and when there really is a performance increase. Also, you should add these variables, these environment variables for Halo exchange and optimized communication between the GPUs. This is also noted in our documentation. As this might be a bit complicated, please contact us for benchmarking. We are happy to help you. Let's use Gromacs on CPUs with MPI support. Here we need to give the number of separate ranks to be used for PME, for the particle mesh eval, electrostatic calculation. You can use tune PME, but it can be tricky. So please get in touch with us. We love to do benchmarking for you. For the number of open MP threads per MPI rank, the NT-OMP flag is used. Here, the number must be tested. It's not as obvious as for the GPUs. And to automatically terminate the Gromacs program, use the max H flag and set it to wall time minus 0.5. So you have about half an hour for copying and ending your simulation. For the CPUs, we recommend you first try the line below and then optimize your parameters. But again, just contact us for benchmarking. Then we go on to some general recommendations and things that we noticed on the cluster. So equilibrations cannot be run on GPUs. You have to use CPUs for that. You should set the time stack for integration for a conventional MD simulation to 2 femtoseconds. It doesn't make sense to set it to 1 femtosecond because you just waste time and power and energy. Here we come also to the output control, which I've said before. You should not let your simulation write more data than you actually need, and you can control this by setting these variables in the .mdp file, which you use with the Gromacs preprocessor to generate the run input file. I told you before that the updates on constraints upload on multiple GPUs only works with constraints on H bonds, so on hydrogen bonds. So if you want to use this option, set constraints in the MDP file. And also use the links algorithm for constraints in Gromacs because it's faster. We have these GPUs available in our clusters. I've included the link to our documentation here. And on TinyGPU, we have the GTX GPUs with 4 physical cores that are connected with 4 physical cores. And that's why you should use the NT-OMP4 in this case. The RTX 2080 has 4 cores plus hyperthreading available, so you can set the NT-OMP to 8 for the RTX 2080, the V100, and also the RTX 3080. And there are also A100s available in TinyGPU with 32 CPU cores. And in Alex, we have the A100s and the A40, each with 16 physical cores available. per GPU. Also, you can see here the difference in the CPUs. In TinyGPU, we mainly have Intel Xeon CPUs and with less cores than the AMD CPUs in Alex. We often come across problems with where to store the simulation data. Here is also the link to our documentation in case you need more information. But in general, use the work directory available under $work, and it points either to home Woody and then the group name and username, or home Saturn or Titan and then the group name and the username. And those are available or accessible via the $Woody home and $Saturn home. There is also Vault available for long-term storage, and this is accessible via the HPC Vault. During the simulation, to be independent from our network and possible network problems, use the RAM disk or the local hard disk, which are both accessible via $TMP DIR. In case you don't know how to use it, please contact us. It's really easy. Just copy all of your input files to $TMP dir and then start the simulation, and then copy or move your data back to your working directory, because the local disk is flushed after the job finishes, so your data is lost. Be careful to remember this and store your data after your simulation is finished. In case you need any help, we have there is the Gromacs documentation, and we also documented special tips and tricks in our documentation. I added the links here. If you have any questions, please contact us via this email address. And we also have a new MD virtual consultation hour where you contact us for the date and the time. And if you have any questions about MD simulations, I will be there, Thomas will be there, and our liaison scientists will also be there and will help you with any problems. And with that, I am coming to the end. This is all I have to say about Gromacs, and I'm happy to answer your questions.
Okay, thanks a lot for this very interesting talk.